Hello! Today we're going to go over some review problems that I assigned during the week of April 13th through the 17th. All the days are kind of just blurring together at this point. Let's get started.
Today I'm going to start with number 1.
A charity fundraiser has a spin the pointer game that uses a spinner like the one illustrated in the figure below. So if we look at the spinner, we see there are 10 spaces. 1, 2, 3, 4, 5, 6 of them have $0. 1, 2, 3 of them have $1, and then there's one space that has $10. A donation of $2 is required to play the game. For each $2 donation, a player spins a pointer once and receives the amount of money indicated in the sectors where the pointer lands on the wheel. The spinner has an equal probability of landing in each of the 10 sectors.
Letter A.
Let X represent the net contribution to charity when one person plays each game once. Complete the table for the probability distribution of X. So essentially they're paying $2 and they can either gain $0, $1, or $10. Let X represent the net contribution to the charity when one person plays the game. So this is how much the charity is going to get every time a person plays the game. So if the person who's playing the game lands on a 0, the charity gets $2. If the person lands on a 1, then they win $1 back, and the charity keeps the other dollar. And then if the person playing the game lands on the 10, then the charity loses $8, right? So all you have to do, and you can leave these as fractions, is just fill out how many spaces out of 10 fit each consequence. So again, zeros are represented by the $2 here, because when they pay $2, and they land on a 0, the charity gets $2. So we count 1, 2, 3, 4, 5, 6. So 6 out of 10. Out of 10, there you go. Probably reduce that to, what is that, 3 out of 5. The next one, $1. Well, 1, 2, 3. That'll happen 3 out of 10 occurrences. Don't have to reduce that one. And then the last one, there's only one spot where the charity would lose $8, so that's 1 out of 10. And that's it for that one.
The lowercase b.
What is the expected value of the net contribution to the charity for one play of each game? So essentially, this is like find the expected value. If you remember, expected value is basically the mean of all of these times, well, it's basically these numbers times their probabilities, and then you add them all together, right? So that's 6 out of 10 times, I don't feel like doing it in my head. So that's doesn't seem right. So 7/10 of a dollar, which is 70 cents, right? So we'll go minimize this. And if you're doing this pen and paper, you can, I guess I should probably type it. So the expected value of the net contribution charity for, good lord, one play of the game is 70 cents. There you go. The charity would like to receive a net contribution of $500 from this game. What is the fewest number of times the game must be played for the expected value of the net contribution to be at least $500? So this is actually probably like the easiest part, because if your expected value is 70 cents, how many times do you have to play a game where the expected value is 70 cents in order to get it up to 100? Well, or 500. So that's just, what number can I multiply times 0.70 to get me up to $500? All you have to do is divide 500 by, where's my division? 70 cents, which, you know, this isn't a calculator. So there you go, 714.2. 714.28. Therefore, you can't play it a fraction of a time, so you have to round up to 1. So therefore, the fewest number of times the game must just be played in order to reach $500 is 715 times. And there you go.
Letter D.
All right, so finally with letter D, we get like an actual like challenge. Based on last year's event, the charity anticipates the spin the pointer game will be played 1,000 times. The charity would like to know the probability of obtaining a net contribution of at least $500 in 1,000 plays of the game. The mean and standard deviation of the net contribution to the charity in 1,000 plays of the game are $700 and 92.79 respectively. So it goes and go ahead and gives us the mean, that's ugly, and the standard deviation. So that's nice. And we also, it's been suggested that, well, if it's given us the mean and standard deviation, chances are we're going to use a normal curve. Now, the catch is we have to explain. And the explanation for this is actually pretty easy because we're only dealing with straight up, just like how do we know we can use the normal distribution. And the reason we use a normal distribution is because our sample size is very large. It's over 1,000. So since it's so large, central limit theorem will apply. So we simply say so there you go. Now we need to find the probability that that it is greater, that our contribution in 1,000 plays is greater than 5,000. So if you're sketching this, you have your normal curve. It's very ugly. Your mean is right here at 700. Standard deviation is 92.7. You can't draw that. And you're trying to find the probability that something is at 500 or more. So you're finding this area over here. So what you do, well, the way we do this is, because we have technology, we use calculator. We say that, well, we're doing statistics. I guess you could use probability as well. And we want, oh my goodness, and we want distributions. And we want a normal CDF because it's a, CDF situation. And we're going from 500 to infinity with our mean of 700 and our standard deviation of, what was it? And we hit OK. And the probability is very high, 0.98, so almost 99%. So like we're almost guaranteed to hit our number. So 0.984, remember that. Remember that. So type. Probably don't have to write that. You do have to put this part. The charity makes at least $500 from the event. I'm sorry, from 1,000 spins, because that's really what we're doing. Spins is 0.984. There you go. All done. You win. Great job.